Hey everybody, sorry I can't be there today. I have a few crises I'm dealing with at home related to ice and stuff like that. Not fun, but it's less fun for my daughter who has water dripping into her bedroom. So we have to take care of that. I hope you guys are staying safe and warm. A couple things we need to do today. We do need to move forward with the physics. So there's two worksheets I'm having you do. The first one, and I'm going to show you a little bit right now, um, is really just how to use these energy transfer diagrams, these LOL charts a little bit. So I'm going to show you how to do a couple of the key problems from this. And then I'll show you how to do a couple when we start getting numbers. We don't really have numbers in this one. It's just practice. So let me just get right into it. So here's the worksheet. Worksheet 2, energy transfer diagrams. So make sure you have that. Okay, so here's the deal. Some things you can't see. Most of this worksheet is fairly clear and easy to read, but some of these drawings are pretty bad. For example, right here, this part, that is a crunched up spring. That is an object that has a completely compressed spring. So that's an important part of this. And notice that it's not moving. So, and then at the end, it's up here on top. And yes, it's moving pretty good. It's got to have some non-zero velocity. It's got to be going pretty fast to make sure it does it on there. So for the initial situation down here, that's the initial situation. We would say there's no kinetic energy. There's no gravitational energy because it can't fall from there. So all we're dealing with is elastic energy. And I'm just going to give it 4 bars. Okay, we'll come back to this energy flow diagram in a second. All right, at the end, there's no more spring energy. The spring is sprung. So 0 bars of, 0 bars of spring energy, elastic energy. Now it is higher, so it's going to have some gravitational, and it's also moving, so it has some kinetic. But if you think about this, we started by giving this thing 4 bars. Why 4? I don't know. We just made it up, you guys. There's no real reason. We just said 4. So we've got to have a total of, if we have 4 there, we've got to have about 4 here. So you can say maybe 2 gravitational and 2 kinetic, 2 gravitational bars because it's up there and it can fall, and 2 kinetic because it's moving. And then everything's balanced. You got the 4 that we started with. You've got the 4 that we started with equal to the 4 that we ended with. All right, 2 quick questions. Some people are asking, well, what's this E internal thing? What is this? That's the same as E therm. It's the same thing. It just means if something heats up, it has more of this stuff. So back in the instructions, you were said to decide if it's frictionless or not. We never talked about that. In a frictionless situation, we're never going to lose energy to heating. But most situations have friction. So let's say there's a little bit. And if that were the case, we would have to say that some of the energy left the system. We lost, I don't know, maybe a half a bar to heat because of the friction. So then what we would do at the end here, we would change this. And we would say that there's still 2 kinetic bars, but now only 1.5 gravitational. And then we lost that half a bar there. So you've got 2, 1.5, plus the one that we lost, it still equals the 4. The 4 is still accounted for. We bring that in. All right. Or you could say that maybe there's a half a bar of heat here and say that no energy left the system. Say it's completely contained system. No energy left. Therefore, it's all accounted with here. So go ahead and change these numbers a little bit. If we said no energy left the system, we could say that there are 2 here, plus 1.5 there, plus 0.5 there. Some of the energy didn't leave the system, it just got stored as heat. All right, so you can watch this over and over again if you need help. There's going to be a handful more of this. I'm going to show you some other ones that's a little bit different. Let's look at this one. Well, no, let's look at this. No, that's not it. What was a good one? I guess we could do this one right here. Okay, notice at the beginning, the height is 0, so that means it has no gravitational energy. It's on the ground. The height is 0. It can't fall. The velocity is 0, so there's no kinetic energy because it's not moving. The elastic energy is 0 because nothing is compressed or stretched, so there's no spring that's going to spring and move this thing along. But at the end, the velocity is greater, the height is greater than 0, so it's going to have some gravitational energy. The velocity is still 0, so there's no kinetic energy. Now here's the weird thing. How do we start with 0 bars of energy and end up with 2 bars of energy at the end? Well, one of the big questions is, how does energy ever get into or out of a system? And we know that's through work. So energy had to go into the system, and how much? Well, 2 bars. How did it get there? By working. And you might ask yourself, who did work? Well, it's clear here. There is a person, some poor sucker. Come on, give me a choice. Some poor sucker here had to push that car up the ramp. Look at them at the end. They're laying down. They're exhausted because that person applied a force for some distance. That, my friends, equals work. If you apply a force times some distance, you got work done. So that guy pushed the car up there. In the process, he or she deposited 2 bars of work into the system, and then it shows up over there. All right, hope that makes sense. So if energy enters or leaves, you got to show it with working. All right, so I'm going to pause this video here, and you guys, if you need help, Sam should be around, and or you can email me, and I'll try to help.